We're almost to the end of the lecture series. I'm not sure what number we are on, actually. I think you did 4 in the fall. We are 5 in the spring here. So we have 2 more lectures. After this one, they're spaced out a little longer, so I'll go ahead and tell you the dates. They will be in your weekly and your monthly. April the 2nd, Alfred Loomis, and then May the 14th, Robert Oppenheimer. So as you can tell, Julius has a little bit of a change for you here, but he'll explain that. And so, Dr. Julius Ziegler, take it away.
Okay, thanks, Susan. You can see that I sort of bailed on what I had promised, and that's because there's more there than I could tackle in an hour and make sense out of. So that we'll have to wait perhaps till fall if people are still interested at that point, and we'll tackle quantum mechanics and relativity both at that point. I'm going back to the end of the 19th century here, and there was a lot going on in terms of trying to understand the stuff that we're made out of. What is the actual structure? The idea that we're made of atoms was pretty firmly held, but nobody had any kind of evidence that atoms actually existed. And so I'm going to carve one slice of how we began to think about and see what we can't see. Several things happened independently and yet somehow intertwined about today's topic. One of them was the work done by a physicist named J.J. Thomson, who was working at Cavendish Labs and who discovered that there was a charged particle, negatively charged particle, that others called an electron. It was the first evidence that at least part of the stuff we're made of, the atoms, had an electric characteristic and could be isolated into single units of electricity. Amazing set of experiments on his part. In the mid-1880s, Heinrich Hertz had done an experiment to confirm Maxwell's prediction of the existence of electromagnetic waves that we can't see. He had shown that light was a form of electromagnetic wave, but Hertz generated the first radio waves, longer wavelength, lower frequency than light. And as we talked about last time, he also discovered what was called the photoelectric effect, which came to be one of the foundational experiments in leading to quantum physics. A few years after Hertz's discovery, as we said last time, Marconi had patented his wireless telegraph, and the modern communication era had begun. On a very different tack, around 1886, let me go forward a bit because we'll wait just a second. A man named William Conrad Röntgen at the University of Würzburg discovered a new kind of radiation that he called X-rays, X for unknown. It would in time be identified as shortwave, high-frequency counterpart of Hertz's radio waves. The ability of that radiation to pass through opaque material that was impenetrable to ordinary light created quite a sensation. So our topic today is going to be Marie Curie. Is one of the most remarkable people in the history of science. And I'll get back to her in a moment. This is Mr. Röntgen, and the device he used was a glass tube filled with nothing, attached to a high voltage electrical source, in this case something called an induction coil, which was invented by Michael Faraday. Thomson had used that device to discover the existence of the electron. He was able to show that, well, let me talk about the device. When you hook that thing up in a circuit, it glows inside, a real pale blue glow. I said there's nothing inside. That's not quite true. It's a vacuum inside, but there's no such thing as a perfect vacuum. So there are air molecules in this thing. Nitrogen, oxygen, all the constituents that we now know of air. And something has happened to cause these atoms to emit light. And it has to do with electricity ultimately. The originator of this device was a man named Crook, C-R-O-O-K-E, and this is called a Crookes tube, and it became a subject of study in many places around Europe after Thomson's discovery. Rinken was working in his lab with a tube like this, and he noticed that a nearby material, what we would call a phosphor, was fluorescing whenever this tube was on, and there was no connection to the tube. Upon some study, he found that the fluorescence was due to the Crookes tube, which was, for his experiment, it had been covered with black paper. He concluded that the fluorescence had to pass through the opaque glass paper, and it must have been caused by the electrical current in the tube. Now, his wife was part of this experiment because she spent the next 7 weeks watching his obsession with this as he worked in his lab. She brought him hot meals when he didn't eat, and pretty much took care of him, left him to his work. And when he needed a hand, she provided one. In fact, her left hand became the subject of Rinken's most famous image entitled Hand mit Ringen, which helped him win the first Nobel Prize in physics in 1901. He wrote to a friend that initially he told no one except his wife about what he was doing, and because as he mailed the discovery, he figured people would say that Rinken is out of his mind. He wrote a brief to many of his colleagues and said, and now the devil was let loose. His discovery made an impact, obviously, as you know, on practical medicine, and in physics it led to a chain of new and really sensational findings. As I said earlier, it was called X-rays because nobody knew what was happening. And though the phenomenon of X-rays is not the same as radioactivity, Rinken opened the door to radioactive discovery. Henri Becquerel in Paris learned about the discovery of X-rays through the fluorescence that materials produce. Does everybody understand what fluorescence is? Fluorescent is something that glows in the dark of its own accord. It's a material that we would call a phosphor, and phosphors have the ability to absorb light and re-emit that light usually at lower frequencies over a long period of time. So they take in energy from light and they re-radiate that energy as light. And things that glow in the dark are generally phosphors. There are many different kinds of phosphors around. So Becquerel had covered several photographic plates with black paper and fluorescent salts. He was going to put the black paper in the sunlight and observe what happened when sunlight struck the photo plates. But it was raining, so he put the wrapped photo plates into a dark desk drawer. And after a few days, he returned to his experiment, unwrapping the photo paper and developing it, expecting only a light fogging from the salts that were surrounded it. And instead, the salts left very distinct outlines in the photographic paper, which you see on the image on the right, suggesting that the salts, regardless of the fact that there was no energy source, no electrical source, nothing, were fluorescing continuously. And in fact, Becquerel had discovered what we call radioactivity. And it turns out that the two researchers who were to play a major role in the continued study of this radiation were Marie and Pierre Curie. Marie Curie, who was born as Maria Sklodowska in Warsaw in 1867, and was raised there during the Russian occupation of Poland. Her parents were school teachers. They were apparently very much committed to her education and the education of her sisters. Her mother contracted tuberculosis and died when Marie Curie was 10. Her father encouraged her tremendously. He at one point lost his teaching job because the Russians were suspicious of him and basically took it from him as they suppressed any kind of education that would lead to education in Polish culture, Polish language, or anything related to Poland. They were determined to destroy Polish culture, as is the case sometimes with occupying nations. Apparently Marie Curie was a prodigy in both literature and math, and her father encouraged her as a teenager to attend what was called the floating university. Sometimes it was called the flying university. It was a free university that moved from location to location every class, which taught physics and natural history as well as the forbidden subjects of Polish history and culture, always trying to stay one step ahead of the Russians in doing so. Now, as a child, there are many anecdotes about Marie's prodigious memory. Apparently, she was somewhat of a prodigy. And at the age of 16, she won a gold medal on completion of her secondary education at the Russian Lycée. But her father, who had not only lost his job, was also not much of an investor, and the family savings had sort of disappeared. So there was no possibility of his supporting her further education. She was not going to be able to go to a university in Poland anyway, because women were not allowed to go to higher education in Poland at the time, again, due to the Russian occupation. She taught in the Free University, reading in Polish to women workers in the factories, and she began to work at the age of 18 as a governess. She apparently made a deal with her older sister, Bronislava, that Marie would help her get through medical school in Paris, and then once she had finished medical school, she would help Marie get her higher education. So beginning at age 18, she became a governess to a very wealthy family in Warsaw. And it turned out that she and the oldest son of that family had a love affair, and he asked her to marry him, and the parents would not hear of it because she was not of the proper class to marry their son. So she lost that job, but she did a lot of other jobs, odd jobs, serving as a maid, teaching where she could, and eventually was able to finance her sister's education at the Sorbonne. She was 24 years old when she left Warsaw for Paris in 1891, and her sister gave her lodging to start out with, and she enrolled at the Sorbonne, the University of Paris. She studied there under some well-known physicists, and She worked apparently all the time. She lived on bread and butter and tea and was often in danger of fainting when she attended classes because she was so weak from malnutrition. She came in first in the license in physical sciences at the Sorbonne in 1893, and she began to work in a research laboratory. And in 1894, placed second in the license of mathematical sciences. Now that doesn't sound like much, except that the license from the Sorbonne is basically a master's degree level completion of mastery of her material. She studied math and French and made ends meet cleaning glassware in university labs. She did ration her intake of food, as I said, until on more than one occasion she collapsed of weakness. But she earned her degree in physics in 1893 and another in mathematics the following year, and then the two licenses beyond that. In 1894, I need to make sure I see what's on there. This is her family, her father and her three sisters. Marie is the one on your left, and then Bronislava and Helena, the oldest sister. This is Marie as a student at the Sorbonne. And this is her love of her life, Pierre Curie. At that point, Pierre Curie was a 35-year-old physicist at a French technical college who had been studying crystals and magnetism. He and his brother Jacques had discovered something called piezoelectricity. That's P-I-E-Z-O electricity. And if you don't know what that is, it's what happens when you stress certain crystals, compress them, they are able to generate electric current. And if you have a gas stove or have had a gas stove and you turn it to the ignite point, you hear a clicking. Those are sparks given off by the piezoelectric crystal in that starter to start the flame on your gas logs or your gas grill or your stove. It was a major discovery, and it brought quite a bit of prestige to Pierre Curie as it was. He was really taken by her intelligence and her drive, and he proposed to her not long after he met her. He wrote in the proposal, "It would be a beautiful thing to pass through life together, hypnotized in our dreams. Your dream for your country, our dream for humanity, and our dream for science." And they were married in 1895 in a civil ceremony. This slide is out of order, but it's good enough. She was wearing a blue dress, one that was practical enough for her to go to the lab after the ceremony and work for the rest of the day. And from then on, she and Pierre followed what they called a, quote, anti-natural, end quote, path that included a, quote, renunciation of the pleasures of life, end quote. They did have some enjoyment, as this picture portrays. Pierre, as a director of a laboratory now, made 6,000 francs per year, which, as best I can tell, was about $30,000 in today's money. And Marie worked in his laboratory for free and prepared for another exam to certify her to teach girls. This was a really unique partnership in all of science. It achieved within a couple of years results of world significance. In particular, the discovery of the element polonium, as named by Marie in honor of her native country, Poland, and in the summer of 1898, and that of radium a few months later, I should say. and it's interesting to sort of dissect that statement a little bit and elaborate on it. Again, the laboratories of those days were pretty primitive compared to modern labs, and I'll make a little bit more out of that in a moment. But she was looking for a subject for a thesis, and she was talking to Professor Becquerel, who was one of her mentors, about radioactivity, which had not yet been called radioactivity, about this new phenomenon. And she decided to study to find out if the property that was discovered in the uranium salts that Becquerel had used for his experiments was to be found in other forms of matter. And she almost immediately discovered that thorium would do the same thing. You might be surprised about the discovery of new elements. You've all seen the periodic table of the elements. Some of you have seen more of it than others. Mendeleev proposed the periodic table in roughly the third quarter of the 19th century. And at the time he proposed it, all the elements were not yet known. He arranged the known elements in a pattern that you know from your elementary chemistry, but there were lots of blanks where he thought an element should be, but nobody had found it yet. Uranium and thorium had only recently been isolated as elements and filled in the table. But there were still blanks in many places on that table when she began her research. The Curie's first daughter, Irene, was born in 1897, and the pregnancy was very difficult, and it ended up with Marie not being able to spend the time in the lab just as she was gathering data for her doctoral thesis. When her mother-in-law died a few weeks after Irene's birth, her father-in-law, Eugene, who was a retired physician, stepped in, becoming the hands-on parent that others expected Marie to be. By the time her second daughter, Eva, was born in 1904, Marie had grown accustomed to the disdain and disapproval of colleagues who thought that she spent too much time in the lab and not enough in the nursery. One of her friends and collaborators actually confronted her. "Don't you love Irene?" Seems to me that I wouldn't prefer the idea of reading a paper by Rutherford to getting what my body needs and looking after such an agreeable little girl. But read the scientific publications she did. The birth of these daughters really did not interrupt her scientific work at all. She was appointed a lecturer in physics at the École Normale Supérieure for Girls in Sèvres in 1900 and introduced there a method of teaching based on experimental demonstrations. And in December of 1904, she became chief assistant in the lab directed by her husband, Pierre. As she began to think about other materials that might, let's see, what do we have? Okay, just again, that's her daughter Irene, and there she is with Eva and Irene. And in the lab with Pierre. You can get a sense of the laboratory.
Who was taking the photograph?
Hmm?
Who was taking the photograph?
Various people. The photography had by 1900 had become a routine kind of thing. So there's no one source. Many of these come from the Curie Museum, but in some of them they don't identify the actual photographer, Bundy. I'll see what else I can find out about that, but there's no single photographer with these. Although you can see in some cases the pictures are the same day. Kind of the clothing is absolutely the same for both of them. For her, I only found images of 2 different dresses in the laboratory in all the pictures that I've found. Now, sure, she had more, but she was not a decorative person in that respect. She became interested in the material called pitchblende, and that's what pitchblende looks like in a pure form on the left, and in a mineral form. There are many different forms of pitchblende in mineral form. The one that she was using was a heavily formed from uranium. It's called uraninite, but it also was a form of pitchblende. She found that the activity, the fluorescing activity, was superior to that of pure uranium, and decided that something else was going on in the ore. There must be small quantities of an unknown substance of very high ability to emit these radioactive rays. Pierre Curie, interestingly here, abandoned his very promising research on crystals and piezoelectricity to join her in the work to resolve this problem. And this is the research that ultimately led to 2 new elements, as I said, polonium and radium. He just devoted himself primarily to the physical study of the new radiations, and she struggled to find the pure materials in the metallic state. And she had help with a very good chemist, one of her husband's former students. And this was on the basis that she received her PhD, the first woman to receive a PhD in France in any discipline in 1903. She was trying to figure out what is causing this radiation. You start with a rock. And then what do? You grind it into dust. And she and Pierre did that in a mortar and pestle. Started with a hammer to break it up, and then used a mortar and pestle to grind it into dust. And then you have to treat it physically. And I'll talk a little bit more about what you had to do to get to purify it. But she wrote in her first paper on these topics that the uranium shows no appreciable change of state, no visible chemical transformation. It remains in appearance at least the same as it ever was. The source of the energy it discharges remains undetectable. That was a paper in 1900. She wondered whether or not the emitted rays were violating a basic law of physics, the conservation of energy. Energy coming from nothing. So she set out to measure the intensity of the uranium's rays, and she adapted an instrument that Pierre had invented with his brother Jacques called an electrometer, electrometer. It was a device to measure very low electrical currents in air, which she was able to do. And so she did that with uranium and then with thorium, which behaved the same way. And then she posed what was, for the time, a really daring hypothesis. The rays emitted might be a basic property of uranium atoms, which we now know them to be subatomic particles released as the atoms undergo radioactive decay. That theory had really radical implications, and nobody had ever suspected such a thing. Some of her colleagues were shocked by somebody daring to make such a hypothesis. One of the contemporary writers that I found said it was a shocking proposal. It was truly amazing and a bold statement because the atom was thought to be the most elementary particle, one that could not be divided. It further meant that atoms are not necessarily stable. And so Curie's hypothesis would revise the scientific understanding of matter at its most fundamental level. But she was puzzled by data that showed that the intensity of the radiation emitted by uranium and thorium was greater than expected based on the amounts of the elements she knew that she had in her samples. There must be, she concluded, some unknown substance very active in these minerals. And she wrote in her own letter, "My husband agreed with me, and I urged that we search at once for this hypothetical substance, thinking what with joint efforts a result would be quickly obtained." Well, in 1898, she identified one of the substances and, as I said, named it polonium. And 5 months later, she identified a second new element, which the world came to know as radium. She described them as radioactive. That's 2 words with a hyphen. But that's the first use of radioactive in the literature anywhere. So, as I said, Pierre was working on this project also. The extraction required tons of pitchblende. Somewhere I've got a slide that makes that point. That's pure radium. And you see that a ton spelled that way is a metric ton, which is 1,000 kilograms or 2,200 pounds of pitchblende to get less than 1/10 of a gram of radium. And what you had to do was to grind the stuff into a powder because you wanted to dissolve it. You could put that rock into a vat of material and it would sit there for years, but if you put it in powder form, it dissolves more quickly. She dissolved the powder in cauldrons, and I mean literally cauldrons, because they were talking about 50 to 75 pounds at a time of this stuff that they were working on, to obtain barium sulfate and other alkalines, which she purified and converted into chlorides. Then you had to go through thousands, literally, of very tedious crystallizations, adding to this, the dissolving a material, letting the liquid evaporate, taking what was left, dissolving that in something else, and going through this sequence. And she wrote to her brother in 1894, quote, "One never notices what has been done. One can only see what remains to be done." After 4 years, she had barely enough radium to fill a thimble. And she was working in what we would call a sort of dilapidated garage, a shed, with these piles of pitchblende in there, broken windows, poor ventilation, and she was nonetheless able to make sensitive measurements. She calculated the atomic weight of radium so accurately that it remained the standard until very recent measurements of the atomic weight of radium gave it more precision. So in 1903, Marie Curie and her husband Pierre and Henri Becquerel were awarded the Nobel Prize for Physics. The Nobel Prize Committee first considered giving the award sharing the award between Pierre Curie and Henri Becquerel. But Pierre said that basically he wouldn't participate unless Marie was recognized for her role in this. They were sick in 1903 when the recognition was made from radiation sickness, as you might imagine. They had no idea the damage that the daily exposure to this dust, this radioactive dust, was doing to their bodies. But Marie Curie, when they went to the 1905 ceremony to be recognized, you have to be at the Nobel Prize in person. At least in those days you did. I assume you still do. She was not permitted to give the lecture because she was a woman. So she sat in the audience with Lord Kelvin, who was a very distinguished physicist, while her husband Pierre spoke on their research. After the lecture, Lord Kelvin held a luncheon for Pierre. Marie was not invited. And in fact, the person who introduced Pierre made some kind of comment, and I've read it, but I couldn't find it to quote it for you. But basically it said something about Marie being his helpmate, when in fact she was the driving force. And he clearly recognized that and made it clear to others. Unfortunately, and it really unfortunately in many respects, during a driving rainstorm in 1906 in Paris, Pierre stepped off the curb and into the path of a rapidly moving carriage and was killed by the horses as they ran over him. Really bitter blow to her. But it was also a decisive turning point in her career. So she decided that she would devote all of her energy to completing the work that they had started together. In May after his death, a month after his death, she was appointed to the professorship that had been left vacant on her husband's death, and she was the first woman to teach at the Sorbonne. In 1908, she became a professor with a title, and in 1910, her fundamental treatise on radioactivity was published. In 1911, she was awarded a Nobel Prize for chemistry for the isolation of pure radium. So she is not the only double Nobel Prize winner, but she is the only person to win Nobel Prizes in two different scientific fields, and be recognized both in physics and chemistry. In 1914, she saw the completion of the building of the laboratories of what is known as the Institut de Radium, or the Radium Institute at the University of Paris. This is a photo taken at or near the time of her second Nobel Prize. She was gaining international recognition. This is a picture of what is called the first Solvay conference. Solvay conferences were a product of the imagination of Max Planck and the money of a Belgian chemist named Ernst Solvay, who sponsored these things. And basically they were a gathering of the intellectual elite in physics from around the world, which in this case was basically Western Europe, to talk about problems in physics and chemistry. And this particular conference was held in 1911. It's the first one, and it was designed to consider the remaining problems of understanding radioactivity. Now, notice that I haven't said anything at all about the radioactive emissions. I mentioned X-rays, but X-rays are a product of rapidly decelerating electrons. Those Crookes tubes, you basically had a beam of electrons that was flowing from the negative terminal down to the positive terminal, and when they hit that positive terminal, they decelerate rapidly. And Maxwell's theory said that accelerating electric charges emit radiation. And that's the way most of the X-ray machines that you use are getting their radiation. It's an electromagnetic phenomenon, period. It is not the same thing that is happening in these fluorescent radioactive materials. By the time, well, actually shortly after this conference, within the next 10 years or so, Ernst Rutherford, who is the tall guy standing in the back right with a mustache. The really distinctive black mustache with Rutherford. Big burly guy. Rutherford was discovering the nature of, or was using 3 different forms that had been isolated of this radiation. 2 of them were particles that were emitted. A positively charged particle that was named alpha radiation because it was the first one discovered. A negatively charged particle that was named beta radiation, and a electromagnetic particle ray called a gamma ray. All of these things were emitted from the nucleus of an atom. And all of them are spontaneous, and so far as we're concerned at this point, nobody had stimulated yet an artificial radioactivity. Her daughter, Irene, was the first one to find artificial induced radioactivity. But basically, you can think of it like this. The nucleus, which Rutherford actually discovered in his lab, is composed of particles that we call protons and neutrons. And there's a certain balance that needs to be struck between the number of protons and the number of neutrons. If there are too many or too few neutrons, then the nucleus isn't happy, and it sort of hiccups and spits out a negative particle and becomes another material altogether. It's a natural radioactive decay. And for the naturally occurring elements, it starts at uranium, and that decay process ends up as lead after many, many different decays, moving from material to material to material. So that was what they were hypothesizing about at this conference. Now you can see Madame Curie. There are several, at least 6 or 7 future Nobel Prize winners in this group, and others whose names are known to just about anybody who's taken an upper level physics or chemistry class. Very famous group of people. Notice that she's the only female. Now, fast forward to 1927, and this is one of the most famous physics pictures that exists. There are 17 Nobel Prize winners in this group. Still only one woman. There is one American that I can think of. Arthur Holly Compton is I think, the only American that's there. And I can point out many of them, but you can find this picture online very easily. But it's very famous. Einstein was in both of them. Rutherford was in both of them. Dirac, Heisenberg, de Broglie, and all the major players in quantum mechanics, Niels Bohr, are all in this one. And this was a conference on quantum mechanics. But the fact is that she was immediately prominent. Now, let me talk a little bit about a different aspect of her life. In 1901, as I mentioned, and I don't think I mentioned the date, she and Becquerel wrote a paper reporting on the physiological effects of radium rays, as they were known. And before those the properties of X-rays and their biological effects were really known, a year later, X-rays were used by a Frenchman to treat a patient who had breast cancer. And that was based on an observation by another scientist that uranium salts accelerated the healing of some skin lesions. This was an accidental discovery, not something that was intentional, but he noticed that these uranium salts had an effect, a biological effect on skin lesions. And so the Institute of Radium was founded in Paris, as I mentioned, with her as a director. And she spent much of the rest of her life. Well, this is a visit with Einstein when actually this is 1911, and you can look, if you look at her, she's very frail in that picture. Anyway, she spent much of the rest of her life working on radium and its biomedical effects. She and Pierre did not patent the technique they actually used for isolating the radium from pitchblende. And so within 5 or 6 years, there were many companies, mostly in America, but certainly in Europe, who were manufacturing radium. And she was supplying radium for research from the 1.5 grams that they had managed to ultimately purify in her laboratory. So researchers in both the United States and in Europe who were doing medical research were using small amounts of radium in coming from Curie Institute. And in fact, at one point she was pretty much out of radium because she had distributed all of it and was not about at her age to go back through and do it again. But the interesting thing about it is that during World War II, she was very instrumental in the use of X-rays, X-radiography, World War I, on the battlefield. The Radium Institute was in full operation, and it became a universal center for these kinds of studies. And this is one of her field X-ray units. There's another one. And on the battlefield, they could X-ray chests and so forth and see where shrapnel and so forth was and treat it. But then this kind of thing began to happen. And if you go back into the 1930s, 20s, in this country, radium salts they were all the rage for doing anything. Here's another one for radium water. And people were only slowly beginning to realize the real dangers of radioactivity. Now, most of you are old enough to have perhaps gone into a department store and a shoe store and stuck your feet in a device and wiggled your toes. So it's not been that long ago that people were very cavalier about radioactivity. These are radium watch dials. And these are the women who painted them and who licked the brushes to get sharp points on them day after day after day, and who paid the price for the radiation damage that was done. Anyway, she was not yet fully accepted, by the way. In 1911, she was denied election to the French Academy of Sciences by 1 vote. Émile Amagat said, quote, "Women cannot be part of the Institute of France," end quote. So she refused to have her name resubmitted for nomination and refused to allow the Academy to publish any of her work. The press attacked her for her daring to be a candidate for membership in the French Academy. Not long after that incident, a newspaper editor alleged in print an affair between Marie Curie and a married scientist who had been one of her husband's students. He denied the charges, and the controversy ended when the editor and the scientist arranged a duel. but neither one fired. And years later, Marie and Pierre's granddaughter married the grandson of the scientist with whom she may or may not have had the affair. But it was quite a scandal in Paris, as you might imagine. I mentioned earlier her daughter, Irene, who married a French physicist and who continued to work in the field of radioactivity throughout her life and was awarded the Nobel Prize. Her husband, Frederick Joliot, hyphenated Curie, and she got the 1934 Nobel Prize for their discovery of artificial radioactivity. In 1921, accompanied by both daughters, she made a trip to the United States. She didn't want to make a trip to the United States. She did not want any kind of publicity. But a young American woman convinced her that she could raise enough money to purchase radium for the Radium Institute if she came to this country and gave lectures. So she reluctantly agreed, and she traveled all the way across the country with a hugely popular series of lectures, all of them sellouts. And at the end of it, President Harding presented her with a gram of radium that was bought as a result of a collection from American women. So she went back literally across the ocean and on an ocean liner holding a vial with a gram of pure radium in it. She gave lectures in Belgium, Brazil, Spain, and Czechoslovakia. She was made a member of the International Commission on Intellectual Cooperation by the Council of the League of Nations. In 1932, in Warsaw, a Radium Institute was created, and her sister Bronislava was the first director. One of her outstanding achievements was to have understood the need to accumulate intense radioactive sources, not only to treat illness, but also to maintain an abundant supply for research in nuclear physics. And until the advent of particle accelerators in 1930, that was the only way you could get radioactive materials to study, was through the accumulation of them in their pure form. The existence in Paris at the Radium Institute of a stock of 1.5 grams of radium over several years had made a decisive contribution to the success of experiments undertaken between 1930 and 1935. The work that Marie Curie did, and along with her husband and colleagues, was done in ignorance of, as I said, of its effect on human health. She and her daughter Irene contracted leukemia, apparently induced by exposure to high levels of radioactivity. Her notebooks are still so radioactive that they cannot be handled. Marie Curie's health was declining seriously by the end of the 1920s. Cataracts contributed to failing vision. She retired to a sanatorium with her daughter Eva as her companion, and she died of pernicious anemia, also clearly an effect of the radioactivity. She and Pierre were both buried in a cemetery just in the Paris suburbs, and only a few years ago, 2011, I think, maybe a little earlier, Francois Mitterrand had her her and ashes, along with Pierre's, moved to the Pantheon in Paris, which is where Napoleon's buried. And this is the tomb. And the ashes are highly radioactive. The tomb is lead-lined. Her contributions to physics have been immense, not only in her own work, the importance of which is demonstrated by the Nobel Prizes, but because of her influence on subsequent generations of nuclear physicists and chemists. She and her daughter Irene wrote the entry on radium for the 13th edition of the Encyclopedia Britannica. She's the first woman to be buried in the Pantheon, and her office and laboratory at the Curie Pavilion of the Radium Institute are preserved as the Curie Museum. And I'll stop this with just a couple of quotes from Madame Curie. We have, as a nation, largely forgotten the value of fundamental science over the last half century or more. And you never know what's going to come out of a particular understanding of nature. Just one other comment before I stop. Did you notice anything as you looked at the pictures of her facial expressions? Absolutely. The only one in which she's smiling is there standing by that bicycle. She's a very serious person. And those who knew her well indicated that she did have a sense of humor, but it's not something that was readily displayed. She was driven to do her science, and she did it. And as an absolutely remarkable person. If you would like to know more about her, there are excellent documentaries on Netflix and other places. There's a made-for Hollywood movie with Greer Garson playing the role of Marie Curie. That's biographical, a little dramatic, especially in her speech to the Nobel Prize assembly and for Nobel Prize in Chemistry. And the biography written by her daughter Eva is a standard. It's as good as any biography you'll find of her. So with that, I'll stop, and if you have questions or comments, I'll respond. Yes, Bill?
So when did they really truly understand the danger of this stuff?
I don't know that you can put a point on it. I mean, obviously, they did not understand it in the 1950s particularly, at least not widely. I'm sure there were voices in the literature saying, this is a two-edged sword. Radioactivity has this peculiar ability to heal and the ability to cause damage. And I remember, when I took physics in high school, we were made aware that was the case, but nobody was concerned about small doses at that point particularly. Nobody was concerned about too many X-rays, even in the 50s. So it's been clearly within the last 75 years that people have really become, in some ways, overly aware. Maybe the bomb and the aftermath of all of the hype and fear of radioactivity related to the bomb began to make people think differently about it. But most people, there is a unit of radioactivity called the Curie, And there's another unit of radioactivity called the becquerel. That's one of them is a standard unit. The Curie is not. It's a historic unit. And something that has the activity of 1 Curie is decaying something like, I have to get my zeros here, 30 million decays per second. So that means if you had a Geiger counter here and you had a 1 Curie source, the needle would not move because it can't move that fast. Or you wouldn't hear it if I had one that clicked. You would not hear it as separate clicks. You would just hear it as a hum. Most radioactive sources that are used in medicine are fairly low dose, millicuries, microcuries. There was a 90 Curie source in Lynchburg for many years that was owned by an operation on Lakeside Drive, whose I think initial name was Applied Radiant Energy, and then became Intertech or something of that nature. And they had a 90 Curie source, which is a very, very hot source. It was not a radium source, but a very active source. And I remember one of my colleagues at Lynchburg College getting called to come over and try to figure out what to do about the algae that was growing on the surface of the source. Totally immune to the radioactivity, but not to an alkali. Yes.
Helen Ann.
Nursing school from 56 to 59. I think I can jabber loud enough, but anyway. And I know that our X-ray department, from taking patients there for chest X-rays or whatever, the technician always stood behind, as she, and still do, this lead-lined area, and had on the lead-lined apron, so
Yes.
to speak. And when I asked, why, they explained, what the absorption, collective absorption, if you're working in that department, of Röntgengrams, which is back there in the 50s, when the doctors would order an X-ray, they'd often refer to it as a Röntgengram. And now I know why, where that came from. But we were made very aware in the mid-50s of the dangers of absorption of too much radiation. So they were very conscious of it in the late 50s, mid to late 50s.
I'm sure that's true in the medical profession, particularly the ones who, I think the first hint that there was a real problem came from the dental profession, where the dentist would actually hold the plate in place, and then you were beginning to lose fingers and hands. And there were articles in the literature, and I don't know the dates of them, but I say that's where it probably began to register with the medical profession that there really is a danger. And again, those are X-rays, which is not in some ways more damaging than some of the radiation from uranium. The positive particles, the alpha rays that are given off by a radioactive entity, don't penetrate things very well. They're big and they're charged, and they come to a halt very quickly, even in air. They just lose their energy and they just disappear. The beta rays penetrate much better, and the gamma rays go wherever they want because they're electromagnetic and they go. So you really have to be very careful. And I know in the 50s the people who worked at Mount Athos and other places all were required to wear dosimeters so that they got a total body reading was it every month, Claude, that you had to deal with the dosimeter? Yeah. Yeah. But it's, you know, you appreciate what X-rays can do for you, and you appreciate if you've had cancer and a radiation treatment that is successful, what that can do for you. And radiation sickness is another matter, and there was certainly a lot of that after Hiroshima.
Any other questions?
All right, just one comment. If there's interest, I will do the quantum mechanics and the relativity stuff in the fall, and try to put it together in a way that makes sense around people. So next time we'll be talking about a little-known person who was probably as important to the success of our World War II effort as Oppenheimer was, but in a very behind-the-scenes way. So I think you'll find that an interesting person to learn about.